Okay, today we'll start the next chapter, which is integration. So let me start with telling what we are going to do. Okay, so the first idea was by Archimedes. So Archimedes lived approximately 300 BC. Okay, so he was the first person who calculated or rather who gave an algorithm to calculate the area of a circle to any degree of precision. He did this by putting regular angons, regular polygons inside and outside the circle. Then the next such algorithm was, of course, developed by the development of calculus a few thousand years later. Of course, after the circle, it comes to the second popular quadratic, which is the parabola. So he calculated the area under a parabola. So for this thing, he couldn't use polygons; he used squares. So we'll talk about his idea. This idea was made precise later by Riemann. Riemann, who lived 1820 something. So let me check the precise dates. 1866. Okay, so you see there were a few thousand years in between. So today we'll start by looking at what Archimedes did using the terminology of Riemann, and that will be an introduction to the idea of integration. And then once we understand what integration is all about, we'll try to develop techniques of evaluating integrals. Okay, so where do we use this? Most of the time, if you need an integral, a computer program will do it for you. But if the integrand is complicated, the computer program doesn't do anything. So it's just because there are certain algorithms the program follows. So it is up to you to break up the problem into simpler parts that the computer can handle. And of course, you have to understand where you need to use integration. Okay, so that's education. You don't have to remember these formulas or anything. You have to remember that there are certain rules, algorithms to calculate certain things, and you have to know where to look up or whom to consult. That's education. Okay, so here, if we come to Riemann, and even after that we go a few more centuries. Well, we don't have many centuries, one more century maybe. Okay, so the first question is, before we start, is what is an area? Okay, so if you think about this, you see that this is a question you must answer. You have to find an explanation for this, and it's not as easy as it looks. So today we say area is a function from some subsets of the plane to non-negative real numbers satisfying some obvious properties. So for example, if you have two non-overlapping sets, each of them has an area, then their total area will be sum of them. Okay, so such nice axiomatic properties, but of course we don't claim that every set has an area. So to start, and you have to normalize it, because suppose that somehow we manage to construct an area function. Now multiply that area function by 5, you have a new area function. Okay, so whatever the area function satisfies, 5 times of that will also satisfy it. So you have to normalize it. Okay, so we normalize it by saying that first we assume, okay, so we assume the area of a rectangle exists and is product of its width and length. So let me just draw a picture because integration is about picture, is A times B. Okay, if this is your rectangle, the area is A times B. Okay, so we assume this, and we realize that if we want to prove this, we have to find something more simpler than this, and there is none. Okay, so we agree that area is this. Then, idea which was used by Archimedes and then made precise by Riemann is then fill out a region by rectangles to approximate, okay, so we'll talk about this, approximate its area. Okay? So one of the axioms we want about area is that if you have two rectangles touching each other like this, then the area of this part is 0. Okay? So the area of a curve is 0. So you can put two rectangles together touching each other. Then the area of this new shape is the area of this plus this. So as far as this area function is concerned, we can consider these as non-overlapping regions, even though they touch at the boundary. Okay, so now with these understandings, we realize that we can put a large rectangle inside the region, and then we can say that if the region has an area, its area is larger than this thing. Then you put smaller and smaller rectangles, and you try to approximate it. Okay, so let's apply this theoretical consideration in practice to the area under a parabola. Okay, so this is what Archimedes did. And of course, I'm using now the notation we use today. So we have this curve, y equals x squared. So it starts like this. So I say y equals x squared. So that, normally Archimedes did this by putting a general number here, but just to illustrate the idea, I'll put 1. Okay, divide 0, 1 into n equal subintervals. Okay, so later on, so 0 is x sub 0. This is x1. Okay, so this subintervals is x0 equals 0, x1, xn is 1. Okay, so we have these things. Let me do one more, x3, and then we'll have dot, dot. Okay. Then put, let me use a different color here to show boxes. Then we'll do this twice. First, we'll put larger rectangles here. Okay, so we put a rectangle here. We go up to the curve and then complete this rectangle. We go up to the curve and complete this rectangle. Okay, we do this. And as usual, we say dot, dot. So let's see what happens at the general point here. Okay. At the general point here, we have xk minus 1, xk, and on top of this, we have this curve. Okay, so here we have this box. Okay, we go up to this curve, then complete this box. So we are looking at this area. Okay. Okay, so what is x1? x1 is 1 over n. Okay, so let me erase this. So maybe I write it over here, it's easier. So x0 is 0. x1 is 1 over n. x2 is, now I go one more 1 over n, so this is 2 over n. Okay, so xk is k over n, and then eventually xn is n over n, which was 1. Okay, so the coordinate of this is k over n. So that I want to know this because then I want to know the coordinates of this. This is the curve y equals x squared. So this is k over n square. So the height is k over n square, and this side is 1 over n. So I know the area of this. Okay, so we'll add up these areas. Okay, so we form now what is called the upper Riemann sum. I'll denote this un. We'll give it a name. Okay, so the area of this thing is base is 1 over n, height is 1 over n square. So this is 1 over n square, plus the second one, okay, base is 1 over n, height is 2 over n square. And I write the general part here. The area is 1 over n times this height, k over n square, plus 1 over n over n square. Okay, so this is the sum. So this is called the upper Riemann sum. Okay, so now we try to simplify this. Okay, so you see that I have n cubed in the denominator, and then inside I have 1 square plus 2 square plus k square plus n square. Okay, so fortunately we have a formula for this, which I can never remember, so I'll just write the formula here. Okay, so the formula for this is 1 over n cubed. So this one is n times n plus 1, 2n minus 1 over 6. Okay, so n's cancel, and you have n plus 1, 2n minus 1 over 6n square. Okay, so our expectation is that if we take larger and larger n, so the boxes will be smaller, will be approaching to the area of the parabola. Why? Because we have such a picture. Let's repeat this one. Okay, so this is just a symbolic thing. So I have, okay, so let me use again these colors. Okay. So I'll repeat this picture first of all. Okay, so we have this thing. I have this area. Okay. Now suppose instead of n, I'm using 2n. Okay, then all these rectangles are divided into 2, and the new rectangles will be like this. Again, now I will have this point, and this point. So I have this square, this rectangle, and then I have this rectangle. Okay. So instead of the blue rectangle area, I'm using this area. So you see that white part, let me emphasize it. Okay, so this area, is shaved off the error. Okay, so this here you see that the area under the curve is this part, and this part is the error. Okay, so this upper part is the error. Here you see now I cut off this rectangle from the error. Now my error is this part, these smaller parts only. So by doubling n, I reduce the error. So we are hoping that if you continue like this, okay, now let's invent calculus. As n goes to infinity, we are hoping that this thing will approach to the area here. Okay, so we take the limit of this. So limit n goes to infinity of un. Okay, so we can calculate it there. The leading term here is 2n squared. This is 6n squared, so 1 over 3. 1 over 3. Okay, so these rectangles, the sum of the areas of these rectangles will converge to 1 over 3. Okay, the best thing we can say here is that the area of the parabola, assuming that it exists, is less than or equal to this number. Okay, so conclusion, the area we are calculating under y equals x squared from 0 to 1. So this is what we are trying to calculate. This is less than or equal to 1 over 3. Okay, because at each stage, the Riemann sum is strictly larger than the area. Okay. So far, we don't know if the area exists or not. We'll decide on that later. So if the area exists, we know that it cannot be larger than 1 over 3. So let's repeat the same argument as smaller rectangles. Let's approach this from below. Okay, so I'll do again this picture. Okay, so next, let's approximate the area from below. Okay, so the picture is something like this again. So we have this, y equals x squared. Okay, so we have again these points. Okay, so here I have the 0 rectangle. And here I go up to the curve and then construct this. Here I go up to the curve and construct this. So we will go like this. And then at the last part here, we have this. So the last rectangle will be this. So we'll be looking at these rectangles. Okay, so again, so 0 is x0, x1, x2, x3. This is xn minus 1, xn. We have dots here. So let's do the general picture again. So this is our curve. So what we are doing is now we are calculating this. Okay. So this is again y equals x squared. This is xk. I'm choosing xk as the part where I go to the point on the curve. Okay. So if this is k, this is as usual. So this is k over n. The coordinates here is k over n and k over n squared. So this is xk plus 1. Okay, so we are trying to find this area. Okay. So again, let me do the other picture also. In the other picture, we will have this. Okay, so we have this area. Okay, so we will have, okay, so first I have this area. Okay, so this goes up to here. Now suppose we have new points as we did over there. So the new points will be this. For this one, I again have this rectangle, but now for the next one, I go a little bit up. Okay, so now again the error is smaller. Okay, so I'm looking at this thing. Here the error was all of this. Now I shaved off something. The error is smaller. Okay, so let us. Here we are again hoping that in the limit we will be very close to the area. So let's do that calculation. This thing is now called the lower Riemann sum, Ln. Okay, so the area here, well, it starts from 0, so let's leave 0 out. Let's start from x1. Okay, so 1 over n times 1 over n squared plus 1 over n here, 2 over n squared plus, okay, so the general one, again, base is 1 over n, height is k over n squared plus. Okay, so where do we stop? Here you see we have to stop here at n minus 1. Okay, so there the base is 1 over n, and then height of this thing is n minus 1 over n squared. Okay, so this is lower Riemann sum. And again, we want to simplify this, so we are mimicking what we did here. The denominator is 1 over n cubed, and what we have here is, okay, so this is what we have, 2 squared up to n minus 1 squared. Okay, so we just put n minus 1 into that formula. This is 1 over n cubed. Okay, I had n there, so n minus 1. Then I have n plus 1, it will be n. Then I have 2n minus 1 minus 1 divided by 6. Okay, so you see again, n's will cancel. I will have n minus 1, 2n minus 1, minus 3. Is that? So that was huh? Plus 1. Yeah, that was I was. So this is 2n plus 1, 2n plus 1. So this is 2n minus 1 divided by 6n squared. Okay, so we see that the limit will again be the same, and we'll draw some conclusions from this. Limit ln as n goes to infinity. In this case, you see is again 1 over 3. So our conclusion from this calculation is that area, whatever it was, cannot be less than 1 over 3. Okay, so now we are in a situation that so we found out if this area exists, it must be 1 over 3. Okay, so at this point we agree that if the lower Riemann sum and the upper Riemann sum converge to the same number, then that number we will agree to call the area of the figure. Okay, so we agree to define this number as the area of the parabola, or rather the area of the parabola from 0 to 1. Of course, a parabola does not have an area, but the region under the area of the region under the parabola. Okay, so region under the parabola. If you want to write everything, it takes too much time. Okay, so that is our first agreement, that we will write upper Riemann sum and lower Riemann sum. And if they agree, we will call this the area of the curve on that interval. Of course, here we are making a few assumptions without knowing. When you write y equals x squared, it's a very nice function. We use very many properties of that without actually realizing. First of all, the function was increasing, so we did not hesitate to say that certain rectangles are under the curve or above the curve. And then we also used, so you can say, okay, let's skip this increasing part. We can still say the property of this point when you choose this point. Okay, so this is the minimum of the function on this interval. When you are doing upper Riemann sum, then you choose the point on that interval where the function takes its maximum. Okay, so here we are assuming that on every subinterval, the function will have a minimum and a maximum. Okay, so that's a property of continuous functions, and then for some non-continuous functions may also have that property, but we are restricting that. So if you want to generalize this idea of area, we cannot always rely on lower and upper Riemann sums. Of course, there are ways to avoid this. You can use step functions, etc., but we are not here to develop the idea fully. We are just trying to understand it generally. So this is where we decide to say, instead of choosing minima and maxima points, choose arbitrary points. Then the Riemann sum will not be necessarily less than or larger than the area, supposing that the area exists. Let us invent a way of saying that this Riemann sum will converge. Let us invent a concept like this. Let us define it. So we will take, the idea we will take from here is that we took these intervals smaller and smaller. Okay, so Let us take an arbitrary point from each subinterval, then take the intervals smaller and smaller, so add millions and millions of intervals. And if this thing converges, whatever that means, we'll try to make sense out of it, then that thing will be the area. Then we'll call it the integral. Here we also use that the function is strictly positive. So we are trying to avoid that too. So how can we avoid this? Here, instead of defining this as the height of a rectangle, we will define this as the value of the function at some point. Okay? Then we don't need whether it's positive or negative. We will stop interpreting it as an area. It will clearly be an area when the function is positive. It will be something else when it is negative. Okay, so let's start that, but then I think we need to talk about partition and other things. Okay, so in general, so we need a few words: partition, sampling, norm of the partition, etc. So we want to develop integration theory for bounded functions, because that's what y equals x squared. At no point we faced an infinite value. There was no vertical asymptotes. Okay, so the function was bounded. Bounded functions on, this was 0, 1. The property we are using for 0, 1 is that it's a bounded function. We will also need the endpoints later on. So even if you say, let's take arbitrary intervals, open intervals, later on when you want to show that continuous functions, they must be integrable because they're so nice, you need the endpoints there. So we put the endpoints there on a closed means endpoints are included, and bounded interval. Okay, so integration theory will be developed for such functions. Some such functions will be integrable, some of them will not. Okay, so let's say, so let f be such a function on a, b. Okay, so we define we need a few words to make life easier. Okay, so remember here we kept talking about we take lots of points, make points smaller at points. Okay, so we want just to invent a word to explain all of that. That's why you need definitions. Okay, a partition. So this is what we want. A partition of AB is a subdivision of AB into smaller intervals, into subintervals. Okay, that is a choice of a finite number of points such that A is x sub 0, then x1 is strictly larger than that, x2 is strictly larger than that, and everything is strictly less than xn, which we fix to be b. Okay? So the picture, everything is a picture. So A is x sub 0, then you have x1, x2, then maybe x3 is here, and this is xn. Okay, so this is b. We are not claiming that the subintervals must be of equal length. They can be of different length. We'll control that by defining the norm of the partition. The norm, so here the definition is partition, here the norm of the partition is, okay, I'll look at these intervals. What do I want here? What happened here is that I took equal subintervals of magnitude of quantity n, and then I send n to infinity, that ensured that all the intervals, all subintervals went to 0. Okay? So here I want to ensure this. So if I say the largest one goes to 0, then the others will also go to 0. Okay? So here that's why I want the norm to be the length of the largest subinterval. Okay? Is maximum of the length x k minus x k minus 1, where k is from 1 to n. Okay? So in this case, the norm is here, this one. This one turns out to be the largest one. Okay, so the idea that will carry from the parabola case to here is, instead of sending n to infinity, or we will again say send n to infinity, but with the understanding that the norm of the partition goes to 0. Okay, so the largest subinterval itself goes to 0. And here the problem was the function was too nice, so we chose points where the function had a minimum and maximum. So we don't want to go into that detail. We don't want to be so demanding from f. So we want to evaluate f somewhere, and that we will call a sampling. A sampling of this partition is a collection of points. So this is x1 star, x2 star, xn star, such that xk star is inside this interval xk minus 1, xk, k equals from 1 to n. So in each interval, I'm choosing a point. So this one will be x3 star. Somewhere here I choose x2 star. Here I can choose this one as x1 star. Okay. Okay, so now you see, instead of all these words, we'll just use these 3 words to express our ideas. So let's form a Riemann sum. Okay. We now form a Riemann sum. Let us call this Sn. Okay, so, I think I need one more definition here. Well, this now notation. Let the length of each subinterval be delta xk. Let the length of each subinterval be denoted by delta xk. Well, this is xk minus xk minus 1. Again, k goes from first interval to the last interval. Okay. So now I form this summation. Okay, so let me k equals from 1 to n. I evaluate the function at this sampling point. Then I multiply it by the length of the interval. Okay? So if f is always positive, we are calculating rectangles. If f is continuous, I can always choose this sampling to be the maximum point of the function on that interval. Then this becomes upper Riemann sum. If I choose xk, these samplings as the points where the function takes its minimum on each subinterval, then it is lower Riemann sum. But in general, you see, we have this this thing called Riemann sum. Okay. So, what do we mean? Now we want the limit. We now want limit Sn as n goes to infinity, where and okay, so here maybe I write it all in sentence. Limit Sn as n goes to infinity, and the norm of the partition goes to 0, okay, for any sampling. Okay, so we summarize these sentences. Okay, so when we say limit, this is what we understand. Okay, so what does it mean? Okay, so this means the following. So this limit is the value of the integral, let's say I, if the following holds. Remember that the limit means that we are getting closer and closer to I as much as we want, so that as much as we want translates to epsilon. So given any epsilon positive, okay, so there exists a delta. So here you see the partition goes to 0. It means that you will take smaller partitions. There is a corresponding delta positive, such that for any partition whose norm is less than delta, and for any sampling of this partition. Okay, so then we can form this Riemann sum. Okay, we are only considering partitions whose norms are less than delta, and then for each subpartition we consider all possible samplings and form Sn. The difference between these two numbers must be less than. Okay, so then the difference between these two numbers is less than epsilon. Okay, so suppose such a complicated thing happens. Okay, so remember that this is always the problem with the definitions. It's very precise. We can see in our mind what is happening, but we don't want anybody to ask us to calculate this, because you see, you have to consider all partitions, and if that is not enough, given any partition, you have to consider all samplings. Obviously, you cannot do this unless you know a lot about the function. Okay, so we will show later on that if f is continuous on a closed and bounded set, we can handle this situation. Okay, so if this holds, so we started with the AB, right? If we didn't, then, okay, we started with the AB. We say f is integrable on AB, and its integral is I. Okay, notation. Okay, so let's come to the notation. So we will use the integral sign. Okay, so notation. So we will say that integral a b f of x dx. Okay, so if we are here, you see the question is now we have to convince you that I need this dx here. Okay, so some books use integral from a to b f of x, and then put a box here and inside x, because at first we try to fool you that the reason why we have dx there is that we don't want you to forget that x is the parameter. Okay, so why should you forget that it's a parameter? But we have to lie you, because in general you don't integrate functions, you integrate differential forms, and this is a differential form. Okay, so actually Actually, what is happening is you have a differential form, dx. dx is a differential form. And this interval a, b, okay, so let me call this delta a cycle. Okay, so this one lives in a different world, this one lives in a different world, and somehow when you hit one to the other one, you get a number, okay? And then you evaluate one over the other, and you get a number. Okay, so this is the actual integration theory, which you start seeing in differential geometry. The explanation is there, but when you come to Riemann integration, you don't need all of the theory here. You just want this theory, and that can be explained without these things. But of course, we have to carry this notation, because later on, well, we will do this in this chapter, when we change coordinates, integral a b f of x dx becomes, let's say, c to d f of, well, not f anymore, a new function here, g of t dt. Okay, so passage from here to here is as follows. Well, let's say x is equal to h of t. The passage here is that you have f of, instead of x, you put h of t. Then instead of x here, if you listen to our word and keep this, at this point, useless notation, here you put h of t again. Then you simplify, then you'll interpret this as differentiation. You have f of h of t, h prime t dt. So this thing turns out to be this function. Okay, so that's why we carry dx there. Okay, so the reason why we are writing dx there is not because you will forget x, but because it will be useful in changing coordinates. And changing coordinates will be automatic when you do this. Of course, here you need some nice properties about this. First of all, it must be differentiable one-to-one, etc. Okay, but we'll come that later. Okay, so this is the notation. This is the notation for integral. Okay, so what we did, for example, we found that the integral from 0 to 1 x squared dx is equal to 1 over 3. This is what we calculated. Okay, so let me see what else we want to calculate. I think we can also calculate the x to the m. Okay, so let's do that because it is fun, and then we can stop after we do this. Okay, so now before we go to that, let's relate this to lower and upper Riemann sum. So note, if f has a min and max on each subinterval of a, b, then we can talk about lower and upper Riemann sums. And of course, then lower Riemann sum is less than or equal to any Riemann sum, less than or equal to upper Riemann sum. Okay, so this is any partition, any sampling. Of course, then, well, okay, then we have to use these partitions, the same partitions here and here. Otherwise, we cannot restrict these things. Okay, so you choose a partition. On that partition, you calculate the lower Riemann sum and upper Riemann sum. And then you choose any sampling. Obviously, the value of the function at that sampling point is larger than the minimum, less than the maximum. So you have this. Okay. Now, I will not go into this, but when Ln and when lower and upper Riemann sums are defined, they definitely have limits. Then limit Ln as n goes to infinity equals n, and limit Un as n goes to infinity u exist. Okay? Because these things are in general, okay, so let's say, so in general, for nice functions, you have L. These things increase, obviously. Okay, check that these things increase. And then here, that is less than or equal to Un minus 1, and less than, let's say, U2, U1. Okay, so you look at this thing. Here you have an increasing sequence bounded by a fixed number. So the general theory of real numbers says that it has a limit. Okay, so I think we mentioned this somewhere. Bounded monotone sequence converges. Okay, and then here we have this thing is decreasing, but it doesn't go to minus infinity. It is cut here by a constant number, so it converges. So you have these numbers, and in general, you have L less than or equal to U. So the theory of Riemann integration is when these things exist, the function is integrable by squeeze theorem if these two numbers are the same. Okay? So f is integrable if u equals L. So in this setup. In this setup means that I'm considering nice properties of f. In particular, continuous will be a very nice property. Okay. So let us do this for, okay, so we have time to do x to the power m. Because you see, x to the power m, instead of x squared, x to the power m satisfies these properties. On every subinterval, it is increasing, continuous, it has a minimum, maximum. So we can avoid this complicated Riemann sum. We just look at upper and Riemann sums, which were easy. Okay, so let us example y equals x to the m greater than or equal to 2 is an integer. So I'll just do the upper Riemann sum because our experience with x squared tells us that the Riemann sum will be the same thing except one term is missing, but when you take the limit, nothing changes. Okay, so let us try to draw a typical thing. So it is something like this. So this is again 1, y equals xm. So what we are doing is we have xk minus 1 here, xk here. So xk is k over n. Okay, so this is xn, and this is 0 is x0. So we look at this rectangle. We'll add up these things. Okay, so upper Riemann sum is equal to this part, as usual, is 1 over n. 1 over n times the coordinates of this point are 1 over n, k over n, and k over n to the power m. Okay, so height is this number, k over n to the power m. Okay, and I add up these things. So let me put the summation sign here. Summation k equals 1 to n. This is my upper Riemann sum. Okay, so you see I can simplify this. This is summation k equals 1 to n, 1 over n to the power m plus 1. And then I have 1 to the power m plus 2 to the power m plus n to the power m. Okay, now we come to, again, another historical fact that Bernoulli, just before he died, he calculated these things because he heard that somebody published a table of sums of mth powers of integers from 1 to n for different values of m and n. Okay, being a mathematician, he got furious. He said, we don't need tables for this. There must be a formula for this. And he developed a formula for this. But he didn't live long. He died. After he died, when they were collecting his table, they found these formulas and they published it. But the formula involves some constants. He called those constants A, B, C. And he said, anybody who stares at this table long enough will see the general rule behind these ABCs. And we are still looking. Nobody has seen the general rule. Well, here the general rule in quotations, because people, what we want is a closed formula. Closed formula may mean two things, but what we mean by closed formula is there is a formula whose length and the number of computations we have to do does not change with n. Okay, given n, we'll calculate the nth Bernoulli number. So if there are 5 calculations, whatever n is, you must do 5 calculations. Okay, that's what we want from a closed formula. We don't have a closed formula yet. But there are double summations. So if you are calculating 1 millionth Bernoulli number, you have to do 1 million calculations. Okay, so question, what is 1m plus 2m plus nm? Okay, so let me, first of all, as far as our calculations are required, it is easy. It is really easy. So let me write really so that you are not scared. Easy to show that, so let's say this is a function f, m is fixed and n changes, that f m x is a polynomial in x of degree m plus 1, whose leading coefficient is, I think, 1 over m plus 1. I'll check. Yes. Okay. So this part you can prove by induction, because we know the formula of sums of integers from 1 to n. M is 1. Okay. Then assume this for m. Check that it is also true for m plus 1. Okay. You have to do some calculations. That's all. Okay. So in general, okay, I think that's. But in general, the formula is, okay, so this f m n business is equal to, let me see where I want to write this, n to the power m plus 1 over m plus 1 plus, I'm writing this because it is surprising that the second term always have coefficient 1 over 2. And the other ones are the mysterious ones. So k starts from 2 to m. You have these mysterious numbers called bk divided by k. M choose k minus 1, n to the power m minus k plus 1. Okay? So here, where these things are in general defined recursively, the first one is minus 1 over 2. And once you know this one, the others are calculated using a recursive formula. I equals from 0 to k minus 1, ki bi equals 0, when k is strictly larger than 1. Okay, so these are bi's are called Bernoulli numbers. So if you go to Wikipedia and look at Bernoulli numbers, there are different notations for Bernoulli numbers, because I think the odd integers ones, if the index is odd, they are all 0. Only the even ones show up, and the even ones show up with alternating signs. So people now have different notations for this. Some people count only the even ones as B1, B2, B3. And some people count only the even ones, but they count it only positive. As positive, they put the sign later on. Some people count this. So every time you want to read something about Bernoulli numbers, just go to the first page and check what they mean by a Bernoulli number. There are at least 3 different ways of, but this is the original Bernoulli. Well, actually, original is Bernoulli called these things A, B, C, D, E, and then you stop there and say you do the rest. So we are still trying to do the rest. Okay, now let's finish this. I know that I'm going to divide this by 1 over m. So taking this over here, I know that first I have 1 over m plus 1 plus, you see this is a polynomial of degree m, and I'm dividing by n to the m plus 1. Okay, so this part, this is 1 over n times something. Okay, now I take the limit as n goes to infinity, so this part will go to 0. So limit un as n goes to infinity is equal to 1 over m plus 1. Okay, you see similarly for lower Riemann sum, because lower Riemann sum misses only this one. We add up these things up to n minus 1. So if you put n minus 1 here, that will again give you n to the power n plus 1, and these things will be complicated. So here, let me say similarly, limit Ln as n goes to infinity. Okay, so integral from 0 to 1 x to the power m dx is equal to 1 over m plus 1. That's what we concluded after taking account all of these things. Okay, so next hour we'll check if all functions are integrable or not. Okay, thank you.